Okay, so since we have now considered opacity as well, so I think now we are ready to talk about the equations of stellar structure in general. So basically, till now we have derived four coupled first order. So we have derived four now coupled first order differential equations. Right. So what are these equations? So these are the four coupled differential equations. Okay, let us name them, say A, B, C and D. So you must remember them, right? So this is the equation of hydrostatic equilibrium. This is the continuity equation. This one we derived previously, right? So basically this one is the equation for radiative energy transport, and then this one is the equation for energy conservation. Now along with these four equations, we also have four boundary conditions for these equations. So let me write it down. Okay, so the first boundary conditions, so we have four boundary conditions as well. So the first one is mass at r is equal to 0 is 0. Of course there is no matter, that's why, right? Again, luminosity at r is equal to 0. How much is this? Come on, there is no matter. Again, so luminosity will be 0. What about pressure? Where is pressure 0? Come on, you cannot say that pressure is 0 at r is equal to 0. In fact, pressure is 0 at the surface, right? So, surface here, radius of the sphere, which we have assumed to be our star, right? Star is assumed to be sphere basically. Okay, now the fourth one is again mass at this surface, and this one is, we know, the total mass of the star. Okay, so this is the total mass of star. Now in reality, at this radius surface here of the photosphere of the star, P does not really go completely to 0. Neither do the temperature and density, and more sophisticated boundary conditions are required, which account for the processes in the photosphere, but we are neglecting them here. So keep this in mind. Okay, now you see, to these four differential equations, we need to add three equations. So we have three more equations. Now, what are these equations? These are the equations which connect the pressure, opacity and the energy production rate of the gas with its density, temperature and composition. So the three equations are basically pressure as a function of density, temperature and composition. Similarly, opacity as a function of density, temperature and composition, and then energy generation rate as a function of density, temperature and composition. Okay, now this one here, we know this by another name, which is equation of state. Okay, note that each of these functions will depend on the composition through the element abundances and the ionization states of each element in the gas, and we parameterize this using the mean molecular weight, right? So we have talked about this previously. Okay, so what do we have? Basically, thus we have ended up with total 4 plus 3 equal to 7 coupled equations, right? And what do these equations define? They basically define the 7 unknown functions. So 7 coupled equations defining 7 unknown functions. And what are they? Well, they are pressure, mass, density, temperature, then followed by opacity, luminosity, and our energy generation rate. Okay, and how many boundary conditions are there? Along with 4 boundary conditions for 4 first order differential equations. Okay, understand? So, as there are 4 boundary conditions for the 4 first order differential equations, so if there is a solution, it is unique. If solution exists, then it is unique. Okay, and this is usually expressed in the form of Vogt-Russell theorem. Okay, and what does this theorem say? Basically, this states that, you see, the properties and evolution of an isolated star are fully determined by its initial mass and its chemical composition. Okay, now these determine the star's observable parameters, that is its surface temperature, radius, and luminosities. A very important point is that 2 variables have been neglected in this treatment, and these have very minor influence on stellar structure. And what are the variables that has been neglected? Well, one is stellar rotation and another is magnetic field. Now, do note that there has been, most of the time, this Vogt-Russell theorem or conjecture has found to be true, but there has been certain deviations as well. So, if we take into account the modifications introduced in the stellar structure by the evolution process itself, which accounts for the deviation, then it is more correct to say that the structure of a star is determined by its mass, number one, by its chemical composition, and also there is another factor which is the age of the star as well. Okay. Now, you see, as a consequence of this Vogt-Russell theorem, so as a consequence, you see, this is where we again started off. I told you previously as well when we started off. You see, what did I tell you? As a consequence of this, we can use as the independent variable this quantity mr. So this can be used as independent variable. Well, what is mr? Mr is basically the mass enclosed by a sphere of radius r. Okay. Okay. So we have talked about the equations of stellar structure together. For the first time we have talked about them, and then we discussed about this uniqueness of the solutions, which is related to the Vogt-Russell theorem. Fine. Now let us talk about how to solve these equations. Okay. As you can see from these equations itself, to find the detailed pressure and temperature dependencies inside a star will require to simultaneously solve these 4 stellar structure equations along with the information of these other informations from these 3 functions: pressure or equation of state, opacity, and energy generation rate. Now of course this is very complicated and this has to be performed numerically. However, you see, we can gain considerable insight into the various general trends by deriving scaling relations. So this is the next topic that we are going to talk about now. So we have our motivation is solving stellar structure equations. These are quite difficult, right? Now I am not going to solve them right now. What I am going to do is I am going to use approximate methods to solve them. So actually you can solve them numerically, but we are avoiding this for the time being. Instead, we will use certain approximate methods or techniques. Now one of them is basically scaling relation. One of the roots goes through the scaling relations. Now before I talk in detail about the scaling relation, let me again repeat what we have observed as observational evidence for the stars. Remember when I started out in our lecture, we talked about the various observational constraints, and there we talked about, in the stellar classification section, we talked about the HR diagram. You must remember this. So let me just quickly recapitulate that. This will be important here. So here on your screen you can see the HR diagram. So what does it show? Basically it tells us, it is showing the luminosity in terms of stellar luminosity versus effective temperature, surface temperature again. And it is important to note that here the axis, you see the axes are logarithmic and the temperature grows to the left. This is important to note that. And what about the dashed lines? I will talk to you. Now you see, this was again independently observed, this trend. This was found independently by 2 astronomers, Hertzsprung and Russell, when they placed measurements of star on the logarithmic plot with axis of luminosity and effective surface temperature. Now what do they find? Basically what is important to observe is that almost all known stars are concentrated in several well-defined loci. So what are they? Here is one of them. Another one is over here. You see this one. Then another one is over here, followed by another group over here. Okay. Now you see, as I was saying, about 80 to 90% of all the stars, depending on what stellar environment one is looking at, they lie in the narrow diagonal strip, this one here. So majority of the stars, majority of stars. And this is known as main sequence. Main sequence. And this corresponds, you must be thinking that, come on sir, you are showing the temperature in the opposite direction. What if we do the temperature in the positive direction? Then what will be the observed temperature? Now let me tell you that here, if we do that, then you will observe that L, the luminosity, is approximately equal to effective temperature. This is TE effective. Okay, now this is how much? T to the power 8. Again, you must also remember that the luminosity of a spherical blackbody radiator, how much is this? It is 4 pi r square into sigma T E effective to the power 4, right? So then what does this imply? These two facts, this is observed and this is the one that we know for blackbody radiator. So from this we immediately understand that hotter stars are bigger, having R of the order of TE effective to the power 4. Okay, now you see the sun, it is around here, is a main sequence star. And since the coolest stars have about half the surface temperature of the sun and the hottest star, so coolest one lie around here, hotter ones around 5 times the solar temperature around here, the radii you see of the main sequence stars are in the range of say 1/4 to 25 times of the solar radii. Right. Now how can you find what are these straight lines? You must be thinking. Well, you see these dashed lines, they show the luminosity temperature relationship. This thing. These are the dashed lines. Here. How can you say, sir? Say this, right? You must be okay. So let me again start with this relation. So as I was saying previously, so a star's luminosity is affected by the surface area and temperature, and if we consider a spherical star of radius capital R, then the luminosity is how much? L is equal to surface area into energy radiated by star per unit area per second, which is sigma T to the power 4. Now let us compare two stars, one this star and with that of sun, and if we do that, then we will obtain this relation. You see, R by R solar to the power 2 and T by T solar to the power 4. So this is obtained from here. Okay, now let me write this relation in logarithmic form. Then what do we have? We have log L by L solar is equal to 4 log T plus twice log R by R solar minus 4 log T. Okay. Now this is of the form, you see, y is equal to mx plus c, and so from here we can make plots like this. Now previously you must remember also this luminosity is in terms of L. Here it is logarithmic plot, but here this is a linear plot, right? This is not logarithmic. Okay, so we have a log plot, log L, and here we have this is increasing and T decreasing. Now if we do that, then from this equation you see we can have certain lines, constant radius lines, and this corresponds to say 100 solar radii. So I am putting R by R solar value and plotting them here. This I am having 1 solar radii, this one is having 0.01 R solar. Okay, so this is how we can do the, and basically this plot is the same. Here also this plot corresponds to, you see, R is equal to 100 R solar. Next is R is equal to R solar. So our sun is around here, and this one corresponds to R is equal to 0.01 R solar. Very small stars, 0.01. Okay. Now, so this is more or less what we observe. HR diagram. So as I was saying, nearly 80 to 90% stars fall on the central diagonal known as the main sequence. Now these stars can range from about a tenth or 1/4, around mass. So previously I was talking about radii. What about the mass? So mass is around 1/10 of the sun to around 200 times. Right. Now these stars, it is important to know that they fuse hydrogen atoms to helium in their cores. Now, along with that, we have got other groups as well. You see, the giant stars, these are giant stars. Okay. Now, how can you say these are giant? Again, you must be thinking. Okay, so let me do a very small, again, a sort of example. So, suppose we have got this HR diagram. This is increasing luminosity, this is decreasing temperature. Again, now suppose in this plot I have 3 stars. This is star, 3 stars. Okay, this is star 1. Okay, this is star 2, and this one is star 3. So the question is, what can we say about these 3 stars? What can we say about them? Fine. Let's see. Now, first let us consider star 1 and 3. So, 1 and 3. Now, they have the same temperature, right? But even if they have same temperature, L3 is more than L1. Okay, now you remember this relationship here. So what do we observe from here? Again, you see, so from this relationship, since L3 is greater than L1, so, and having the same temperature, so this means that R3 is greater than R1. Okay, so this is why I was saying that they are giants, they have larger size. Now, this is about star 1 and 3. Next, what about star 1 and 2? This star, these two. Now, here they have the same luminosity, right? They have the same luminosity, you see. They have the same value. Previously, they have the same temperature, same luminosity. But, you see, temperature of 2 is more than temperature of 1. So, even though they have the same luminosity, T2 is greater than T1. Again, let me now go back to this relationship over here. And so, from there, what can we say? We can say that since L is the same, we can immediately get the idea that R2 is less than R1. So, you see, the defining point is this relationship. So, everything is possible using this black body approximation. Very, very simple thing. So, basically, we are just doing this thing. LA, LB is equal to RA, RB square, and then TA, TB to the power 4. So we are getting all this information just using this relationship, right? Now, so from these two relations, what can we say about these stars? So from these two relations regarding the radii, we can say that R3 is greater than R1 is greater than R2. R3, R1, R2. This means that radius increases while moving up and moving right in HR diagram. Okay, you see, such very simple things can be observed very beautifully using this relationship. Okay, now back to our plot, HR diagram. So the giant stars, they are located at the top right and they have low temperatures but high luminosity. Now when we move further in the HR diagram, we find so these are giants and these ones are supergiants. So when we move further up, we find supergiants. These high luminosity and low temperature stars are extremely large in size, even 100 to 1000 times that of the sun. Now near the bottom left over here, you see, we have the white dwarfs. They are very hot, but their luminosity is very low. So you see, from the very simple example that we have, you can say that their size is very small compared to our sun to have such low luminosities. Okay. Now you see, before I continue forward, let me show you a very nice example of the HR diagram. You see, this HR diagram can be used to give information, very nice information about star clusters. In the diagram that you are seeing right here, you see this is the HR diagram, this is absolute magnitude. Again, same thing, basically luminosity. And here is a decreasing temperature. On the plot, there are, you can see two star clusters. So basically two clusters of stars. One is M67, another NGC 188. You can see that they have very different. They're quite different from each other. So the question is just similar to the previous example that I have shown you, where I considered 3 stars, right? This is the one that I considered. Now, instead of 3 stars, I am considering 2 star clusters. And then I am showing you the HR diagram. And again, the same question is placed before you. And that is, what can you say from this observed HR diagram? What can you say? Now, you see, some very interesting points can be said. Of course, this is why I am showing this to you, right? Now, the first thing is that, you see, this M67 cluster, this has the most massive main sequence stars. And why is it so? Can you say? Let me tell you. So, let me again talk about the old, very simple HR diagram. So here, you can see one very important loci, and this is the one. This is the stellar loci which you can see for the main sequence, right? Similarly, there are another 2 very important stellar loci. Actually, I wanted to show this. That's why I have asked you about the comparison, and that is L proportional to what is the dependence of L with mass. So L to scales as, it is observed that L scales as m to the power alpha. Okay, but alpha is not the same. You see, this alpha, it has a value of approximately 3. for more massive stars than Sun, right? And what about the less massive stars? Well, for less massive stars, alpha has a value of approximately 5. So this is for less massive stars than Sun. Well, you can have consider an intermediate value of 4, but these are the 3 very important loci that we observe from this HR diagram. Now let me come back here. So what I was saying is that M67, this stellar cluster, it has the most massive main sequence stars. Because why? Here you see the main sequence, it extends to more luminous, more larger values to L. And we remember that L scales as m to the power 3 for massive stars, right? And so this means that there are more luminous and massive stars in M67 than NGC 188. So this is the first observation, that M67 has the most massive main sequence stars. What is the next observation? The next observation is, I'm not telling you. Let me show you again a very simple example. Okay. Suppose, let us again assume a star to be a sphere. Then what about its gravitational potential energy? Well, it is just 3 by 5 g m square by r, right? Okay. Now the time tau for which this star will radiate this amount of energy, let us calculate that. So the time for which the star will radiate this energy, well, remember that here we are assuming that gravitational contraction is the only source of energy, and the time tau again for which the star will radiate this energy with luminosity is how much? Is just given by omega by luminosity, and this is just 3 by 5 g m square by r into 1 by L. Now we know that L scales as m to the power alpha, and alpha has value 3 and 5. Let us consider an intermediate value of alpha is equal to 4. Then what will happen? Then you will see, if we use that, then you will see that this tau, it scales as 1 by m square. So tau scales as 1 by m square. So what does this mean? You see, this is a very important consequence. This equation, it states that basically the larger the mass of the star, the shorter its lifetime. This is very strange. Why? Now this is because the fuel consumption gets huge for the more massive stars. Even if massive stars have more fuel, they consume it at such intensely high rates that they don't live as long as lower mass stars, right? Because of high luminosity. The sun will live on the main sequence for 10 billion years. You see, lower mass stars live longer than the sun, and as just I am saying, higher mass stars live much shorter than the sun. So if we take this into account, then what about this example? So as I was saying, you see, what we observe is that because the main sequence of NGC 188, it contains only low mass stars. Here you see the higher mass stars are not there. Why? Because they have already evolved to either white dwarf or giant or supergiants. No high mass stars. So this means that as it contains only low mass stars, so it has longer lifetimes. Low mass stars having longer lifetimes. So this means that this NGC 188, it contains only low mass stars, no high mass stars. And since low mass stars have very high age, so we come to the conclusion that NGC 188 is the older cluster among the two. So you see, we have two conclusions. One is M67 has the most massive main sequence stars. Another, NGC 188 is the older cluster. Okay, so we have now more or less come to the conclusion on the HR diagram part. Now let me talk about the solving of the stellar structure equations, which was our original topic, right? Now you see, I want to do perform scaling relations. Okay. Now, basically, my aim is to derive. So, what I want to do is basically I want to derive the observational forms of the mass luminosity relation. Okay, and also the observational form of the effective temperature and luminosity relation that we have observed in the HR diagram. Okay, this is the reason I talked about HR diagram. So I want to derive this. So how do we do that? So basically we will use the scaling relations, right? So how do we proceed? You see, let us assume for simplicity that the functions PR, MR, rho r and TR, they are roughly all power laws. That means PR follows r to the power beta, MR it follows some other form r to the power gamma, and so on and so forth. Now if this is so, then what will happen to the stellar structure equations? You see, I have written down the first three stellar structure equations, and you will observe that this basically becomes P of the order of m rho by r. This one, it becomes m of the order of r cube into rho, and this one becomes L of the order of t. This here is L, so t to the power 4. Tt is I am also taking of the order of t, so this will become t to the power 4 r by kappa rho. Let me name them. So let this be equation 0, 1, 2. Okay, now basically what I am doing here in the scaling format is basically, instead of solving the differential equation df dx is equal to x to the power 4, what I am doing is just I am writing directly that f scales as x to the power 4. Is it 4? No, x scales as x to the power 5, taking dx also as into account. So x to the power 5. This is what I am doing. Now for moderately massive stars, the pressure, you see, what is it? The pressure is defined by the kinetic gas pressure and the opacity by electron screening. So we have, you see, P gas is equal to R by mu rho into T. So from this relation we will have P scales as rho into T, equation 3. And then using previous equation, previous result on opacity from our last class, so opacity or electron scattering, You remember this was 0.2 into 1 plus this x. So this means that kappa is equal to constant. Equation 4. Now let us equate equation 0 and 3. Then you will see what we will find is T of the order of m by r. This is equation 5. But let me tell you something. This is just virial theorem. How? You remember when I was trying to derive the virial temperature using the virial theorem? So what we did was this 3 by 2 n kb, and this was virial temperature. This was approximately equal to, by virial theorem, half of the gravitational energy. So this is basically half of g m square by r, or half of g m n mean mass into r. Now this n and this n can cut down, and from here you will see that we again get the same old scaling. Okay, fine. Now substituting this, so substituting this in equation 2 and then again using equation 1, let's see what we get. So we have r to the power kappa into rho into m to the power 4 by r to the power 4. So this scales as m to the power 4 by rho r cube. Again this scales as m to the power 4 by m. So this means that L is of the order of m cube. Hooray! We get this. You see, this is what we have observed for main sequence stars. More massive than Sun, right? This is what we observe. So let this be equation 6. Okay, now you see this equation 5 here, this also suggests that r is of the order of m. So equation 5, it suggests r is of the order of m on main sequence. Let's see how is that. Now let us consider a star that is forming from a mass m, which is contracting under its own gravity and heating up. Now the contraction will stop and an equilibrium will be set in once the density and the temperature in the core are high enough for the onset of nuclear reactions. Thus, you see, for any initial mass, R will stop shrinking when a particular core temperature is reached. So what does this mean? This means that the internal temperature is comparable in all main sequence stars. That is, there is a weak dependence on mass and hence approximately constant. And so we have this relation, R approximately equal to M. Now, in fact, detailed models do confirm that the core temperature, it varies only by a factor of 4 over a range of 100 in mass on the main sequence. So now, with this relation R of the order of M, we see that from equation 1 that the density of a star decreases as so. Now from equation 1 we see that density decreases as m to the power minus 2. So this means that more massive stars will have low density. So this means more massive stars have low density and low mass have high density. Okay, now this was, we have talked till now about the intermediate stars. Now let us talk about low mass stars. Now, so for low mass stars, high density, there is high density. And this means that there is a dominant role of important role played by the bound free and the free opacity. So, which means that we will be using the Kramer's opacity law. Remember, in the last class we talked about this. So, this is equation 8. Now, you see, since T is of the order of constant, R is of the order of m, rho scales as m to the power minus 2, then this kappa, it scales as rho or to the power minus 2. Now we will use equation 2. So this time using equation 2, we have, you see, L R divided by kappa into rho. So this scales as R by rho square or m to the power 5. Again, hooray! So this is what we have observed for low mass stars. Right. Now let us talk about the most massive stars. So most massive stars. What about it? Now you see, for them the gas density is very low compared to the radiation pressure. So basically what we have is R by mu rho T plus 1 by 3 A T to the power 4, and this is since negligible, so we can write approximately 1 by 3 A T to the power 4. This means that P scales as T to the power 4. Right, equation 10. And the previous equation was, this was equation 9. Okay. Now, what about the electron scaling? Kappa is constant. So, this will again be the main source of opacity. Now, if we equate this with equation 10 and substitute for T to the power 4 in equation 2, then you will see what we get is this. L is of the order of m. You see, a flattening. So basically, this is again what we observe is basically a flattening of mass luminosity relationship, again which has been observed for the main sequence stars. So we have observed the L dependence on m for low mass, intermediate mass and high mass stars. Okay. Now finally let me talk about the relation between L and T effective. Right, now you know we observe that L is proportional to m to the power 5 for low mass stars, m this low mass stars, this one for moderately massive stars, and right. Now let us make an intermediate slope. That means L is of the order of m to the power 4. Now since R is of the order of m, so sigma Te to the power 4 is equal to L by 4 pi r square, and this scales as m to the power 4 by m square or m2 or L to the power half. This means, what does this mean? This means L is proportional to T to the power 8. Hooray! Again, this is again, so we have reproduced again what has been observed. Right. We have thus seen that the mass versus luminosity relation and the surface temperature versus luminosity relation of the main sequence stars are very simply consequences of the different sources of pressure and opacity in stars of different masses. And again, this is of the fact that the onset of the nuclear hydrogen burning keeps the core temperatures of all main sequence stars in a narrow range. Okay.